So remember, it's about the vectors. When we add or subtract, we convert it to addition and we worry about the vectors. So number one here is addition. We have negative 427. Positive 381 goes the other direction and is shorter. So it's telling us our answer is negative, and it's the difference between the absolute values. So 427 minus 381 is going to give us 46. Is that right? Yep. So negative 46. Number two, we're multiplying. When we multiply or divide, we combine the numbers like we normally would, and then we put the correct sign on it. Here, 25 times 32 is 800. A positive times a negative is a negative. So negative 800. Number three, since that's subtraction, we are going to convert it into addition. So the negative 83 doesn't change. Minus 52 becomes plus a negative 52. So now our vectors, we've got negative 83, negative 52 goes the same direction. So it's obviously negative, and since both vectors go the same direction, we combine, we add the absolute values to give us 135. So it's negative 135. And number four, division. We combine the numbers. 128 divided by 8 is a 16. Then we worry about the sign. A negative divided by a positive is negative. So negative 16. Any questions on those? Okay. So to start off today, we're going to start off talking about variables. We kind of mix variables in with our operations as we work our way up through for this class. A variable is nothing more than a symbol used to represent an unknown. Most of the time it's an unknown value. For this class, it's always going to be an unknown value, but it could be other things. Typically for us, we use letters. A, B, C, D, usually X, Y, and Z are the most common ones we use. But it could be other symbols. As you get into geometry, if you were going into trig or anything like that, you would see these symbols. Those are the Greek letters, alpha, beta, and gamma. They're often used to represent angles, or you might have theta, phi, those other symbols to represent unknown angles. The main reason we use them is because we run out of our standard letters, so we need more variables to put out there. These variables can take on many forms. One form is just a generic representation. We talked a little bit last week about some of the properties of numbers. One of them we talked about was commutative. This applies only to addition and multiplication. So that 3 plus 8 is equal to 8 plus 3. Well, because that's true for any two numbers, we don't have to write the numbers in there. We can use variables. A plus B is equal to B plus A. In this case, A and B can equal any number. So that's why this is a generic representation, is because it can be literally anything that can be represented by those variables. It can be used in a formula. In electronics, voltage is equal to current times resistance. So that formula tells us that once we know those values, we can plug them in and calculate. If we know that the current is 3 amps and the resistance is 20 ohms, we can then find that voltage is 3 times 20, or 60 volts. We can have it as a placeholder. What that means, now again here, this one up here, it could be, each of those could be any value, but here it's more so waiting for a value to be assigned to it. It's waiting for a value to come to it. This placeholder might appear something like this: 3x plus 7 equals 49. Here it has only one value. And we should be able to figure out what it is. So those are different ways that our variable is used. To start out today, I want to talk a little bit about just using them to represent an unknown value, a generic value kind of. And what we're going to be looking at is translating standard phrases, and we're going to refer to it as translating English, into algebraic phrases. So into an algebraic representation. So take a look at this and how that would work. Let's say I give you the phrase a number increased by 4. Now there are 3 things going on in this problem. One of them is the obvious one. We have a 4. Something is happening with that 4. The lesser obvious ones, we have a number. The number is our unknown. We have to represent that with a variable. We could use x, we can use n. Those are probably the most common ones. We can use p, whatever letter we want to. Now, a side note, when you're working in my math lab, be very careful, because somewhere in the problem, it will specify a letter to use. So it'll give you the phrase, and then in parentheses, it might say, use W to represent the unknown value. So anyway, here, we're going to use just the variable x to represent that unknown number. The third piece of information is some sort of an operation. What is going on between that unknown number and our 4? What operation is implied here? Addition. Increased by means addition. So x plus 4, or a number plus 4. What are some other phrases that might imply that exact same symbol, x plus 4? I'll put the easy one out there. A number plus 4 would be x plus 4. Can you think of any others? Well, we're going to say we want that same symbol though, the generic number x plus 4. So a phrase that would imply that exact same symbol. Okay, 4 added to a number. Or a number added to 4. Now notice here it says the 4 comes first here, but 4 added to still implies the plus 4. The 4 is being added at the end of the number. Four more than a number. Could be x plus 4 or 4 plus x. Doesn't matter whether we have x plus 4 or 4 plus x. Oh, we just mentioned that commutative property again. When we add, the order of the numbers doesn't matter. Now, one that's a little trickier for people is this one. 4 greater than a number. A lot of people, when they see that, they want to do this. 4 greater than x. It doesn't say 4 is greater than a number, though, does it? It just says 4 greater. 4 greater than a number is the same as saying 4 more than a number. That 4 is being added to it. So that is still x plus 4. Again, it could be n plus 4, y plus 4, whatever variable you want to use. And there are several others that we could put out there for x plus 4. So here, 7 less than a number. Less than a number implies what operation is happening? Subtraction. 7 less than a number implies it's the 7 being subtracted. Once again, we'll represent the number with x. So x minus 7. Now again, this is one that people get confused. They think the 7 comes first in the phrase, that it has to come first in the symbols. And it does not. This is not 7 minus x. It's x minus 7. 7 less means 7 is being subtracted. Other phrases that might indicate x minus 7. Okay, a number take away 7. It's a good one. Any others? A number minus 7. Ah, there's a big word, the difference of a number and 7. The word difference is actually a very important word. It is the result of a subtraction problem. So the word difference implies subtraction. For addition up here, what name applies to addition? Other than difference, it would be there we go, the sum of a number. Of course, that would be 4 for that one, a number and 4. Again, that word sum implies the result of an addition problem. Others for x minus 7. A number reduced by 7. Seven subtracted from a number, all sorts of phrases like that, right? So we can come up with a bunch of phrases that would represent x minus 7. A number repeated 5 times. What operation does that imply? Well, repeated 5 times is just 5 times x or x times 5. Or you could do repeated addition. But remember, repeated addition is the definition of multiplication. So 5 times x, most of the time we just write 5x without the times in there. Can we think of any other phrases that would represent 5x? Five times a number would be one of them. Any others you can think of? A number multiplied by 5. Just like we have sum for addition and difference for subtraction. Anybody know what the result of a multiplication problem is called? The product of a number and 5, or the product of 5 and a number, either one would be the same. And of course, there are other phrases we could come up with for 5x. If I have a number split 3 ways, what algebraic symbols does that imply? Division, good. X divided by 3, or we often write it as x over 3 in that fraction form. That also implies division. What are some other phrases that might indicate x over 3 or x divided by 3? Well, there's a number divided by 3. Three into a number. Any others? For addition, we have sum. Subtraction, we have difference. Multiplication, we have product. For division, we have quotient. So the quotient of a number in 3 implies the number divided by 3, or x divided by 3. So these first several examples we just talked about are all a single operation. Given the phrase, it's usually not too hard to find the operation that it implies. You do have to be careful about order. For addition and multiplication, it doesn't matter, but for subtraction and division, it does. For subtraction and division, you do have to make sure, is it x divided by 3 or 3 divided by x? You have to be very careful in the wording. But where it gets much more difficult is when there's more than one operation. So for example, you might have five times a number increased by 9. What's that going to look like? Well, increased by 9 implies addition, plus 9 of some sort. 5 times a number is just multiplying. So 5 times the number would be 5x. Increased by 9 would be plus 9. How about this one? 9 more than 5 times the number. Nine more than something implies addition. We're adding 9 to something. 5 times the number still means 5x. Even though those phrases were quite different, they represented the same algebraic expression. How about this one? 5 times the sum of a number and 9. This one looks like it might be the same as those first two. There's a very important difference. This is 5 times a number. This is 5 times the sum, the total. So that's implying that the addition happened first. So the sum of a number and 9 is x plus 9. That happened first. Then it was multiplied by 5. Remember our order of operations from last week? Multiplication happens before addition. So in order to make the addition happen first, we have to put it in parentheses. So the sum happens first, and then it is multiplied by 5. I want you guys to try these next two in your notes. Seven less than the product of 3 and a number, and 3 times the difference of a number and 7. I'll give you a couple minutes to work on those and we'll talk about them. So the first one, 7 less than the product of 3 and a number. What'd you come up with? 3x minus 7. Very good. 7 less than implies that 7 is being subtracted from something. That's the minus 7. The product of 3 and a number is just 3x. The bottom one, 3 times the difference. Well, 3 is multiplying something, but it is the difference of x minus 7. So that has to go in parentheses. Any questions? Okay. What does that mean? 8 to the third. 8 to the third power is how it's pronounced. How would we calculate it out without a calculator? 8 times 8 times 8. Good. 8 to the third power is defined to be 3 eighths multiplied together. Or 512 for those of you wondering. Now that one wouldn't be so bad to just punch into your calculator as 8 times 8 times 8. But if I had something like 2 to the 11th, we don't want to be trying to punch that one in and trying to count as that 10 twos or 11 twos or how many you put in. So there is a key on your calculator. Depending on your calculator, most of you will have a key that looks like that. It's called the caret key. On the TI-30, it's on the left side about halfway down the keyboard. On some of your other calculators, it might be an X to the Y key or a Y to the X key. And the way that key works, to do 2 to the 11th, both of those keys work exactly the same. You type in the 2, press that key, then the 11, and hit equals. Hopefully it gives you the answer of 2048. Give it a shot, see if it works out. It worked? Let's try a little bit bigger one. 5 to the 6th. See if you get 15,625. Yes? Okay. Anybody have any questions on how their calculator works? Now, a big application of this is our powers of 10. 10 to the third power is, careful, 10 times 10 times 10, just 1,000. 10 to the fifth power, 100,000. A shortcut that we were taught way back when is if it's 10 to a power, whatever this power is how many zeros are in our answer. 10 to the third, it's 1 followed by 3 zeros. 10 to the fifth, it's 1 followed by 5 zeros. What's 10 to the 0? A lot of people will say 0. This is another one. It doesn't make sense to have 0 tens multiplied together, does it? It's kind of like our multiplying two negatives, where the basic definition doesn't work. So, just like we did with the negatives, we look for a pattern. 10 to the third was 1,000. 10 to the second was 100. 10 to the 1 is 10. Well, notice here, when the base of our exponent is 10, when we reduce the power by 1 from 3 down to 2, the result is divided by 10. We go from 2 down to 1. 100 divided by 10 gives us 10. So if we keep going with that, 10 to the 0, we reduce the power by 1. What's 10 divided by 10? 1. 10 to the power of 0 equals 1. Now this pattern is very similar for any number. Any number to the power of 0 equals 1. So 47 to the power of 0 equals 1. Anything to the power of 0. X to the power of 0 equals 1. Be careful with that because I have somewhat of a twisted sense of humor. You might at some point on a quiz or a test run into a problem that might look something like this. What's that equal? 1. Why does it equal 1? Because the whole thing is to the power of 0. So everything that goes on in here doesn't matter. It's to the power of 0. It equals 1. Yeah, there's a reason why I stand at the door and listen for revving engines in the parking lot before I leave. Okay. Those powers of 10 have already been very relevant to some of the things we've done. Remember we looked at those place values last week? You had the ones, the tens, the hundreds, and the 1,000s, the 10,000s, and so on. Well, 10 to the power of 0 is 1. 10 to the power of 1 is 10. 10 squared is the hundreds. 10 to the third is 1,000. 10 to the fourth is the 10,000s. 10 to the fifth is the 100,000s. 10 to the sixth is the millions, and so on. Those are our place values. In fact, when we took those numbers and wrote them out in that expanded form or full form, something like 627, instead of writing out hundreds and tens and ones, we could have done this. 6 times 10 squared is 6 hundreds, plus 2 tens would be 2 times 10. We don't have to write the 10 to the 1 there. The 1 is implied. Plus 7 ones. Well, we could do 7 times 10 to the 0 or just plus 7. The times 1 is kind of implied. With this written out like this, it shows us the similarity between our whole numbers and what we're going to look at next, which is algebraic numbers. I'm going to show you an algebraic number. Like that, 6x squared plus 2x plus 7. Notice the similarities here between that and the 610 squared plus 2 times 10 plus 7. Here, the place up on top here, the place values were ones, tens, and hundreds. Ones, tens, and 10 squareds. Down here, the place values are ones, x's, and x squareds. That number there, 6x squared plus 2x plus 7, is really just a single number with 3 digits. It is written out in that expanded form so that we can see the place values. That this is the ones digit, this is the x digit, this is the x squareds digit. Just like in whole numbers, we have the ones, the tens, and the 10 squared, or the hundreds digits. So these algebraic numbers like this are going to behave exactly the same, or pretty close to exactly the same, I should say, as our whole numbers. A couple of differences we'll run into. One is, of course, these are always written out in expanded form because the x squared can't be implied by a position because that only works for powers of 10s for the place value. The second is if I have an integer, negative 329, every digit of that number is negative. This is negative 300s and negative 210s and negative 9 ones. In an algebraic number, every digit can be positive or negative on its own. I can have 5x squared minus 3x plus 9. Where you can see here, the 5x squared and the 9 ones are both positive. The 3x is negative. It's negative 3x. So it's possible to have single digits positive or negative on their own in the algebraic numbers. The other thing that's possible in the algebraic numbers is to have more than one digit in each place value. There is no carrying from one digit to the next in algebraic numbers. In whole numbers, you couldn't have a 1 and a 3 in the tens digit. In algebraic numbers, we can have more than one digit there in that place value. Any questions? Okay, so if I take a look at something like 5x squared plus 7x plus 8. Now I put it in parentheses here not because it's making me do anything there first. I'm putting in parentheses just like I did with my negative numbers to just separate them out from the rest of the problem. So 5x squared plus 7x plus 8 plus 3x squared plus 5x plus 1. This is just like adding whole numbers. Now, many of you were probably taught a shortcut of just pull out the parentheses, get rid of the parentheses, and go at it, combine the digits. But we can go ahead and do this just like we did with whole numbers. We write out the first one. Then we put the second one below it, and we add. And remember, when we add or subtract, we must have the same name. So we'll start at the right and work our way back to the left here. 8 ones and 1 1 make 9 ones. 7 x's and 5 x's make 12x plus 1 plus 5x squared and 3x squared makes, careful, 5 plus 3 is 8x squared. Just like adding whole numbers. Now, of course, the big difference is that individual digits can be positive or negative on their own. We can have 3x squared minus 9x plus 11 plus 2x squared plus 5x minus 8. So we write out the first number, the 3x squared minus 9x plus 11. Then again, we write the second one under it, making sure we line up. The 2x squared goes under the 3x squared. The 5x goes under the negative 9x. And the negative 8 goes under the 11. And we're adding. So now we have to be careful with our negatives. What is 11 plus negative 8? Positive 3. Very good. Negative 9x plus 5x. Well, negative 9 plus 5 is going to be negative 4, and we keep the name of x. 3x squared plus 2x squared. 3 plus 2 is 5, and we keep the name of x squared. I'm going to have you guys try one in your notes. Seven x squared minus 4x plus 3 plus negative 3x squared plus 7x minus 5. Give you a minute to do that one. So we'll write it out. 7x squared minus 4x plus 3. We put the negative 3x squared under the 7x squared, positive 7x under the negative 4x, the negative 5 under the positive 3, and we are adding, what is 3 plus negative 5? Minus 2, very good. Negative 4x plus 7x, positive 3x, and 7x squared plus negative 3x squared, 4x squared. How many of you had that? Any questions on that? Okay, we're a minute early, but let's go ahead and take our break here. Now let's come back at 9:29. So then the next step is to add with these algebraic numbers, to subtract with these algebraic numbers. So let's take a look at something like 3x squared plus 9x plus 5. And we're going to subtract from that 5x squared plus 2x plus 12. So now once again, we line things up. We're going to write out the first one. And then for the second one, we'll put the 5x squared under the 3x squared, the 2x under the 9x, and the 12 ones under the 5 ones. And now we are subtracting this time. So 5 minus 12. If I would like to, I could rewrite that as 5 plus a negative 12, which turns out to be negative 7. Nine x minus 2x is positive 7x. 3x squared minus 5x squared. Negative 2x squared. Perfect. That gets a lot more confusing when we throw in negatives. Now there were negative results here, but notice none of the pieces here were negative. So as we throw in negative digits within each number, it can be more complicated. Now many of you, by the way, were probably taught to do this. Drop the parentheses here, right? Then over here, you drop the parentheses, change this to plus, then you change the sign of every digit inside that parentheses. That's what a standard algebra course would usually teach. Again, that is a shortcut of just doing the long subtraction. But if that's how you were taught, that works, and please feel free to keep doing it if you like. So what if we have 5x squared minus 9x plus 2 minus 3x squared plus 7x minus 11. So again, we're going to go ahead and line things up. We've got our 5x squared minus 9x plus 2. We're going to put the x squareds under the x squared, so 3x squared goes under 5x squared. The 7x will go under the negative 9x, and the negative 11 ones will go under the positive 2 ones. And we have to remember we're subtracting down the columns. Now this one gets tricky. Remember, we are subtracting. This is 2 minus a negative 11. We are subtracting. 2 minus a negative 11 is the same as 2 plus 11. So that would be positive 13. Here, the x is going to, we're going to keep the same name. It's a negative 9 minus 7, which is the same as negative 9 plus a negative 7. So that is a negative 16. Now 5 minus 3 we can probably do is just 2x squared. So this is where the negatives start to drive us nuts. I'm going to have you try one in your notes. 3x squared plus 5x minus 8 minus 7x squared minus 12x plus 3. I'll have you give that one a shot in your notes. We'll talk about it. So we'll go ahead and write this out. Again, we're subtracting down each column. Negative 8 minus 3 is negative 11. Very good. 5x minus a negative 12x. Positive 17x. Good. And 3x squared minus 7x squared. Negative 4x squared. Perfect. So again, be very careful with the negatives. What happens when we run into something like this? Well, we notice there's something missing there. What it is, there's an analogy between that and this. 502, if we were to write that out in expanded form, we would write 500s, or 5 times 10 squared, plus 2 1s. We would not write plus 0 10s, would we? Because we don't need to. But it is still there. If we're going to add or subtract with it, we have to have it in there, don't we? Same thing happens here. We don't write the 0 x's in there, but that place value is still there. So we write this out, that's 7x squared. We have to put in plus 0x. And then minus 4. Then 3x squared minus 5x plus 3. And we are still subtracting. Negative 4 minus 3 is negative 7. Now here's the tricky one. 0 minus a negative 5. Positive 5x. Good. And 7x squared minus 3x squared. 4x squared. So in your notes, I'm going to have you try. Two x squared plus 5 minus 7x squared minus 3x. I'll give you a 2x squared plus 0x plus 5. We're subtracting. Oops, I screwed up. I don't know if I put it there and it disappeared or if I never put it there. That should be a 7x squared minus 3x. You guys want a minute to redo it with that there? Or do you guys assume that? Okay, so that's 7x squared minus 3x plus 0 we'll put in there. 5 minus 0, of course, is positive 5. 0x minus a negative 3x, positive 3x. And 2x squared minus 7x squared, careful, minus 5x squared. There we go. Now, before we can talk about our other operations, we need to talk a little bit about this. If I do 10 squared times 10 to the third, remember 10 squared means 2 tens multiplied together. 10 to the third means 3 tens. If I multiply them all together, how many tens do I have? There's 5 of them being multiplied together, or 10 to the fifth. The shortcut is you can just combine the powers. 2 plus 3 makes 5. So 10 to the 7th times 10 to the 11th would be 10 to the 18th. Good. 7 plus 11 would be 18. It applies to variables too. X to the 8th times x to the 3rd is going to be x to the 11th. Now it requires us within these exponents to look at the two pieces. That exponent has two pieces. This number here is referred to as the base. This here is referred to as the power. So when we are multiplying exponents, as long as they have the same base, the effect is we just add the powers. If I have y to the 9th times z to the 5th, I end up with y to the 9th z to the 5th. I cannot add those powers because those were different bases. I had a base of y in one exponent and a base of z in the other. I must have the same base. Now, if it were p to the 8th times p to the 5th, can I add the powers there? Yes, because they're the same base. 8 plus 5 is 13. So as I go to look at multiplying these algebraic numbers, I have to be able to work with those exponents like that. So if I have something like 8x times 3x, just like we talked about early last week, we combine the counts. What's 8 times 3? 24. And we also combine the names. X times x is x squared. Very good. Now we couldn't add these together because they have different names, but when we multiply, we don't need the same name. 7x times 4y, we'll combine the count. 7 times 4 is 28. And then we also combine the names. X times y becomes xy. A little bit of a side note, when we write these like this, where we're combining two variables or multiplying two variables like that, we should try to put them in alphabetical order. It is not wrong if you don't, but it's kind of a math grammar thing. It's more proper to put them in alphabetical order. So if I have something like this, 5x squared times 8x to the third, I multiply the counts. What's 5 times 8? 40, and then I multiply the names. X squared times x to the third, x to the fifth. I just add their powers. What if I have more than one name, more than one variable? Well, I still combine the counts. 4 times 2 is 8. Then I combine the names with each variable or each name separately. X times x is x squared, x to the second. Y times y squared, y to the third. There we go. We might have 3x to the 8th, y squared, z to the 5th, times 9, x to the 3rd, y to the 5th, z to the 4th. Just like before, we combine the numbers, combine the counts. 3 times 9 is 27. Then we'll do each name or each variable separately. X to the 8th times x to the 3rd, 11th. 8 plus 3 is 11. Y squared times y to the 5th, 2 plus 5 is 7. Y to the 7th. And then z to the 9th. Good. 5 plus 4 is 9. Now, so far, all we have done is multiply numbers with a single digit. If we want to go to a single digit times a multiple digit number, like 2 times 43, the way we did that with whole numbers is we wrote out the larger number on top. Usually the number with the most digit goes on top. 43 times 2. We did 2 times 3 is 6, and 2 times 4 is 8. 43 times 2 is 86. Now, I purposely did that one so there was no carrying in it, but you guys hopefully know where the carrying comes into it. The reason I did that one with no carrying is we don't carry in algebraic numbers. If I have 5 times 3x plus 7, I can just write that as 3x plus 7 times 5. 5 times 7 is 35. That's a positive 35. And 5 times 3x is 15x. I can multiply that out longhand just like I can with whole numbers. Now, most of us were taught a shortcut for multiplying things that look like this, called distributing. Distributing is simply taking this number and doing the rainbows. 5 times 3x is 15x, and 5 times 7 is 35, so 15x plus 35. We get the same answer either way, and this method here is a little shorter, takes up less paper. This is actually how it is done. That's the long form of multiplication with algebraic numbers. We'll come back when we get to even larger numbers and we'll look at that method again. Most of the time, we're going to end up shortening it up like this just because where we're going to be doing this kind of multiplication, we're going to have restricted space to keep our answer within. So if we had 7 times 5x minus 2, tell me what to do. 7 times 5x is 35x, and then 7 times negative 2 is minus 14, negative 14. Now you'll notice also that I've been kind of going interchangeably between a negative and a minus here. Because remember, an operation operates on the number that comes after it. So when I see this subtraction here, that goes with the 14 that comes after it. So that means, remember, if we go back to what we discussed last week, subtraction becomes plus the opposite. That means plus a negative 14. It's just shorter to write it as 35x minus 14. When you go to use it, sometimes you need to be able to switch back and forth between those notations. They both mean the same thing. But sometimes it's easier to think of it as a positive 14 that's been subtracted. Other times it's easier to think of it as a negative 14 that's been added. And we'll look at that as we go on here in some of our other problems that we'll run into. We might have more than 2 digits inside the parentheses. We may have something like this, 4 times 3x squared minus 9x plus 5. It works the same way. We could pull it out if we wanted to and multiply it out the long way, but we don't need to. We can multiply it right inside here with the distributing. 4 times 3x squared is 12x squared. 4 times negative 9x, negative 36x. And 4 times 5, positive 20. We've got the same result over here. 4 times 5 is positive 20. 4 times negative 9x is a negative 36x. 4 times 3x squared is a 12x squared. Any questions? Okay. The next step, if we have 2-digit numbers, now we did something like 43 times 21 last week, where this was 4 tens plus 3 ones. This is 2 tens plus 1 1. And remember, we said that when we multiply, since we don't need the same name, we can multiply every digit in the other number by every digit in the first number. Well, after seeing whole numbers written out in long form like that, multiplication of our algebraic numbers is probably going to look a little more familiar, similar. We might have 3x plus 5 times 2x minus 7. The long way to multiply this out here is to write it 3x plus 5 over 2x minus 7. And we're going to multiply it out. Negative 7 times 5 would be negative 7 times 5 would be a negative 35, right? You're thinking plus. Yeah. Negative 7 times 3x is a negative 21x. 3 times 7 is 21. Positive times negative is negative. And there's an x. Now, just like with whole numbers, we put in a 0 there when we move over to the next digit. 2x times 5, positive 10x. 2x times 3x, 6x squared. Then we add negative 35 and 0 is negative 35. Negative 21x and 10x is a negative 11x. And the 6x squared. Many of you were probably taught a shortcut called FOIL. FOIL is just a shortcut to simulate this and make it a little shorter. This is the long way or the full way of multiplying them out. In FOIL, the F stands for first. So you multiply the first digit in each number. 3x times 2x is 6x. The O stands for outer or outside, whichever prefer. 3x times negative 7 is a negative 21x. I stands for inside or inner. 5 times 2x is 10x. Now, some of you are taught to put the 10x out here. I usually put the positive 10x below the 21x so they stay lined up. And then L stands for last. You multiply the last digit in each. 5 times negative 7 is a negative 35. So we do have negative 35. Negative 21 and 10 is negative 11x. And 6x squared. So the FOIL saves a little time, a little space. All it is a shortcut for doing this. Remember, I told you with whole numbers that we could do the FOIL method with whole numbers too if you wanted to. The one thing I don't like about FOIL is it only really applies if you have two two-digit numbers. If we have something like this, 5x minus 3 times 2x squared minus 9x plus 11, FOIL doesn't really work there because you got that middle digit. It'd be FOIL. But obviously you can adjust it to make it work, repeating your distribution. If we did the long multiplication, of course, I always put the number with the most digits on top. It's really no adjustment. You're just multiplying it out. What we're going to get, I'm going to do the FOIL. 5x times 2x is 10. X times x squared is x to the third. 5x times negative 9x. What's 5 times 9? 45. So we have negative 45. X times x is x squared. And 5x times positive 11 is a positive 55x. Move over to the next digit. Negative 3 times 2x squared. Negative 6x squared. Good. Negative 3 times negative 9x. Positive 27x. And negative 3 times positive 11. Negative 33. And we can combine our like terms. Negative 33 just stays negative 33. Positive 55x and positive 27x is a positive 82x. Negative 45x squared and negative 6x squared is negative 51x squared, and the 10x to the third. Any questions? We can do order of operations with these types of problems. When I look at this, what number did they have? Is that a 5 or 3? That was a 3, wasn't it? I don't know what it is with this new computer. Sometimes when I switch ink colors, things disappear on me. Okay, so I have a problem like this. 3 times 7x minus 5 plus 4 times 3x plus 8. This is really just an order of operations problem. It's no different than having something like this. 2 times 35 plus 6 times 18. You have to do the multiplications first, and then you add. Same thing here. We have to do the multiplications first, and then add. Now it's confusing because you see those parentheses, and we're used to parentheses being closing symbols. Here are the parentheses being enclosing symbols. In other words, are they asking us to do anything inside of them first? No, they're not. But we should check. Is there anything to do inside this parentheses? No. 7x minus 5, there's nothing I can combine. How about this one? No. 3x plus 8, I can't combine anything. So there's nothing to do inside either parentheses. So now I go back to the larger picture, remembering that this is multiplication between those numbers in the parentheses. So I will multiply. 3 times the 7x minus 5. Well, 3 times 7x is 21x. 3 times negative 5, negative 15. Now, technically, I should do that multiplication and then rewrite the rest of the problem. From here on out, I'll probably just move over and do this multiplication without rewriting the whole thing. It works. But technically, I should do it this way. So now I've got 4 times 3x, which is 12x, and it's positive, so I'm going to put in a plus 12x. And 4 times 8 is 32. Now I can go ahead and add. Now I could pull these out, do the 21x and negative 15, 12x and positive 32 like that. I can add like that if I want to. Probably quicker in this form to just combine the things that have the same name. I have 21x and positive 12x make 33x. I have negative 15 and positive 32, which will make positive 17. That's what I would have got over here if I would have added them this way. I want you guys to try one. Try that one in your notes. Some of you may not be done, but let's take a look at what you have so far. So here we have 7 times 2x, which is 14x, and 7 times negative 5, which is negative 35. Now, the second part, there's 2 ways you can handle it, and I'm going to show you the easiest way. Rather than 4 times the 5x minus 3, we treat it as negative 4. Negative 4 times 5x, negative 20x, and negative 4 times negative 3 is a positive 12. Now we can combine 14x and negative 20x, negative 6x, good, and negative 35 and positive 12, negative 23. So negative 6x minus 23. Any questions there? Okay. Our last skill for the day. The command we might be asked to do would be evaluate. The ones that we're doing up here, the command might be either simplify or combine. When we get simplify or combine, that implies that we might not get down to a single answer. Something like this, negative 6x minus 23, fits in with that. It's simplified, we've combined things, but we haven't got it down to a single numerical answer. When we're given this command to evaluate, our answer better be a single number when we're done. Now to evaluate 5x minus 2p, I have to be given values. So let's say we're asked to evaluate 5x minus 2p for m equals 3 and p equals 5. So what that means is we replace those variables, those letters, with the values that were given for them. So 5x squared becomes 5 times 3 squared. Minus 2p becomes minus 2 times 5. And now we go ahead and calculate it out. Order of operations, there's no enclosing symbols. We do have an exponent, 3 squared, which is 9. Now we have multiplication, so we're going to go left to right. 5 times 9 is 45. Then we'll do the 2 times 5, which is 10. 45 minus 10 is 35. So we evaluated that to 35. What if we're asked to evaluate that same expression again, but this time for m equals negative 4 and p equals 3? I'm going to have you try that in your notes quick. So we put the numbers in. What is negative 4 squared? Positive 16. I'm going to show you something on your calculator in a little bit with that. So now we have to do the 5 times 16, which is 80. Then we'll do the 2 times 3, which is 6. 80 minus 6 is 74. We have to be careful punching this one in the calculator, because if we'd done this, 5 times negative 4 squared minus 2 times 3, my calculator is going to give me a very wrong answer. Negative 86 is not the correct answer. The reason being is this part right here, the negative 4 squared. It'll try to tell me that it's negative 16. Well, any number squared has to be positive. Negative 4 times negative 4, a negative times a negative is a positive. Why does that say negative 16 then? Well, because the calculator follows a strict order of operations. A power, an exponent, comes before a negative. So it does the squared first, then puts the minus in front of it. To truly square a negative on the calculator, you must put it in parentheses. So negative 4 squared is a positive 16. So to do this problem on the calculator, it would have been 5 times parentheses negative 4 squared minus 2 times 3 to get the 74 that we had. Okay, there is a new quiz that should be available in my math lab now. Should have probably opened up, I think, at 8 o'clock this morning. It will be there until 11:59 p.m. tomorrow. That is Tuesday. So you can do it either this afternoon, well, actually any time today, or tomorrow. The quiz does allow 2 attempts. That is not 2 attempts per question. When you go through, you do each question. Once you submit the quiz, it'll grade it, and you can go back and look at your questions and see what you got wrong. And then you can go ahead and attempt the whole quiz again if you would like. It does not let you just go back and redo the ones you got wrong. It makes you do the whole thing. There is no risk to doing it again. If you take it a second time and you do worse than you did the first time, the system will automatically take the highest score. So unless you get a perfect score the first time you take it, there's no reason not to try a second time. But I do recommend that you look at the ones you got wrong, go back and review them before. You don't just jump in and do it again. Unless it's one of those obvious mistakes that you see it and you know, I should have known better. There will also be a new homework. Homework 2, which will be due Wednesday in class. Any questions? Okay, well, that brings us to our end of new material for today. We'll see you all on Wednesday for another happy lecture.